Hi, my name is Tomer, and I'm here to present a joint work on machine learning-based detector referred to as Meta-ViterbiNet. Meta-ViterbiNet employs previous ideas, such as the parameterization of Viterbi, called ViterbiNet, with meta-learning in order to accurately detect in rapidly time-varying channels both synthetic models as well as the realistic cost model. This is the agenda for this talk. First, we'll cover the specific problem setup, including the transmission protocol and the channel. Then I'll briefly present the machine learning-based detector called ViterbiNet. At last, I'll present our meta-learning framework for ViterbiNet, discussing on how to improve detection in a data-driven fashion for selected channels. And of course, we'll see some results for this approach. So let's begin. Wireless data traffic have grown exponentially over recent years with no foreseen saturation. 6G communication would require high adaptivity to both new channels and to new environments. To withstand the connectivity requirements, many researchers look to incorporate machine learning into classical communication blocks, including detectors, which is the focus of our work. However, there's a big difference between conventional deep learning applications in vision or NLP versus the application to physical layer communications due to both the dynamic nature of wireless channels as well as the need to achieve near optimal performance. An assumption that machine learning takes is that the training distribution must match the test distribution. Obviously, this assumption is hard to make at many domains and specifically at communications where the distribution can change frequently. The questions that we set to ask is how to train a machine learning detector in a fast varying environment. Before getting to the approach, let me present several assumptions. First, the channel has a memory of L, meaning that Y, the received channel vector, depends on the current and L-1 previous symbols, where a single symbol is denoted by S. This is a widely used model for representing multipath channels. Additionally, we transmit in words or blocks of bits, and the channel follows a Markovian relation, as in here. Our detector is given by the mapping S hat, and the detector's goal is to minimize the bear over all bits. Well, obviously, the maximum likelihood detector for this case is the Viterbi detector, which is also very efficient and works in linear complexity over the block. But it has maximum likelihood performance only when the branch metrics are calculated accurately. And this assumes full CSI, channel state information. So when the channel is nonlinear, for example, one should take another approach. Another such approach is the ViterbiNet, which keeps the same basic architecture of Viterbi, but replaces the probabilities calculation with a neural network, learning the mapping to branch metrics from the data itself. Now, when the channel changes over time, we can learn in a semi-supervised approach. The transmitted data is first encoded, and after the receiver, if it is correctly decoded, it is encoded again and used for training the detector in real time. This helps the detector to follow a changing channel, indicating a distribution shift. Visually, let's look at the given protocol of transmitted frames, where each frame holds a single pilot block, followed by multiple data blocks. So first, we train on the pilot and use the network to detect the first data block. Then we train on the first data block and use the network to detect the second data block. And this continues to the next frames as well. But what if the channel changes rapidly? So the training on current block isn't optimal for detecting the next block. Using the naive online training, we missed on important temporal relations, using only a very short-term history rather than a longer one. Looking on the broad picture, the previous ViterbiNet solution correctly employed the coded communication blocks for learning as the data. The architecture of ViterbiNet is also fit for this issue. The last piece left untouched is the online training, which fails on these hard varying scenarios. Our approach employs a meta-learning approach to deal with such channels, adjusting the training algorithm part. A quick reminder, Model-Agnostic Meta-Learning, or MAML in short, is a method for training the hyperparameters of the network, such as the initial weights. Given a batch of tasks, we want to learn the weights such that we adapt much quicker to a new task, which is mostly a low resource task. So now we can ask how to use it for our case. In training, we assume to hold a dataset of known pilots over a quick fading channel. We first divide them into subsequent pairs. We take the first pilot of each pair and calculate some loss minimizing parameters for ViterbiNet. Then we take these parameters and use them to calculate the loss over the second pilot of each pair. Aggregating over all such pairs and minimizing the sum leads us to the empirical optimal initial parameters for ViterbiNet. These parameters are optimal in the sense that training on the current block will minimize the loss or the error on the next block. And this is the actual task we have in the online evaluation, where we have only the current block and train on it to detect the next block. We work under the usual cross-entropy loss to minimize the bear. Specifically, what we'll do in evaluation is after every block, load the meta-learning weights and train over the current block, using the output weights to detect the next block. We'll also hold a buffer, which is updated with the correctly decoded samples, and periodically update the meta weights in a similar fashion to before. This way, we can embed even fast varying temporal relations, given that there is some periodicity in the channel. Moving to results, we use the channel of length 4 with 4 taps and over a transmission of 300 blocks, each having 136 coded symbols. We train on the left channel and evaluate on the synthetic right channel. we tested 3 approaches: joint training, regular online training, and the meta-training on 2 different detectors, the ViterbiNet and a model-free LSTM detector. You can see that at 12 dB of SNR, our approach, Meta-ViterbiNet, adapts better to varying channels, indicated by the lower aggregated bear. Considering the end results over multiple SNRs, you can see that our approach improves in up to 0.5 dB on online ViterbiNet, while still being far from the lower bound, which is Viterbi with full CSI. We are still showing a large improvement. Moving to a more realistic scenario, we also test our method on a cost simulated scenario. Here, our method beats the online ViterbiNet by a margin of 0.6 dB in high SNRs. So to sum up, our main contribution is the improvement of the training algorithm. We modified the MAML algorithm for a time series data, where we use the current coded block for learning the best weights for detection of the next block. Our novelty incorporates different ideas for a meta-driven, robust detector, showing excellent results on a synthetic and a cost channels. Please refer to our paper for more details. And we also published our Python code on GitHub, and you are welcome to check it. Thank you.